Yeah, I mean, this is math. Hopefully everything makes sense in this course. Yeah? All right. We're going to get started. Katya, a quick comment before we get started. Go ahead.
If 1 over t was negative, you wouldn't be able to do the cosine.
If 1 over t was negative. If this was like negative 1 over t in here or something.
You're saying that
It would still work. You'd just be like cosine inverse of negative t, right?
so what are you saying that it can't work?
And actually, the cosine inverse of negative t would be fun. That's the same thing as the cosine inverse of t. Right? Oh wait, no, I said that wrong. It's cosine. Excuse me. Say again your comment though, Katya.
You just told didn't you just say that you can't use that, like you can't use the cosine inverse all the time to replace the secant inverse?
You could. I think she was saying like, say you were just taking the secant of something else, secant inverse of something else in life. Could you just not ever remember this formula and instead be like, well, I don't really care. I'm just going to treat that as being this, and then take the derivative of this. And she's right. Like you could do that, but then you'd have to deal with the change. You'd have to like clean it up every time you did it, you know. So. And you'd also have to think about the sign errors that you might have, sign plus or minus. You might be off by a positive or plus or minus. All right, quick question.
So you can remove the absolute value bars if it's positive?
If you know it's positive. So we did that here because we know it's positive. And I did that once in our lesson on Friday because we had like a 1 over, or we had like a t to the 4th or something like that. And I knew that regardless of the value of t, it was going to be
And so
positive.
if you don't know, you should leave the bars.
If you don't know, you should leave them there though.
And then you
Absolutely.
can't do all that multiplication.
And then you might not be able to do such cool things, which would make Camber really sad. He loves to simplify, and that would be sad if you could work that through. All right, so we're happy with the warm-up. I'm going to make it go away now. Pretty sophisticated warm-up here. Sorry to stretch you like that. Okay. So today we're going to talk more generally. We're going to generalize kind of on some of the thoughts. Really, it's the same section. We did do some derivatives and inverse functions on Friday. We just restricted our attention to only trig functions. So we have a more general thing to say today, and we're going to start by doing a little thought experiment, a little algebra 1 thought experiment. I'd like you to think about what the slope is of this line at 6,3. Good job. You're done. Okay. What's the corresponding point on f inverse? That is, what point do we have on the inverse function? 6. And what's the slope at that point? -3/2? No. All right, so that might take a little more work. This one, what was the answer up here? 2/3, of course. Everywhere, the answer is 2/3. What's the corresponding point on f inverse? 3/6, you said. Okay, but no, we haven't quite had an answer to this yet, and I would like to ask, what do you notice about your answer once you have one, but no one has one yet. So take a second and make sure, turn to your neighbor and tell them once you figure it out what the answer to C is. Give you a second to collect your thoughts. Anyone have a hint for it? You could find the inverse if you want. Right?
Oh, yeah.
3 halves. 3 halves. Oh, yeah.
You have everyone 10 more seconds to think about it.
Why is it white? I get white.
Not that I know, but you can look around. All right, Derek and Co. What did you guys come up with? What do you think? 3 halves. Do you have any? And do you guys agree over here? Over here? Yes. Over here? With us? Okay. Anyone have a conjecture then? In D, what would you like to conjecture? Or what do you notice? Is there anything you would like to notice? I don't know.
Is the slope of the original function the inverse of the slope of the inverse?
What do you mean inverse?
Oh, I think the sine inverse of the cosine.
Okay, all right. Do you agree with her conjecture?
Yeah.
Or maybe? Maybe? That is, the point is, could we generalize? This is just a literally little cute example. Let's do one more, see if we can come up with an even more powerful conjecture. How about this? This is for calculus students now. What's the slope on this function at 2 comma 4? Figure that out quickly. I have the same series of questions here. Right? What's the corresponding point on f inverse? What's the slope on f inverse at this point? And then let's think about the conjecture again. So go through those real quick. Again, with the tables here. Figure out what the slope is. Use some calculus here. Use some calculus.
What's the corresponding?
Wait, give us the
I'm talking about.
No, they don't appear there at all, Amy. Forgot I had them up there.
You got like,
They may be written up there.
I was just telling Garrett, Garrett, like, how do you know? And I was like,
Pretend they weren't up there. So do the same analysis with x squared though. All right, I'll call bankruptcy. All right, so how do you get m equals 4 here for the slope of that right tangent line? What are you doing, of course? Yeah, just power rules, plug in 2, and you happen to get 4. It's unfortunate an example actually because this is also the y coordinate, but whatever. Okay. So the slope is 4, and then you found the corresponding point on f inverse is of course 4, 2. And now how do you get the slope there? It's not obvious. It's not as quick to get that. Maybe. What are we taking the derivative of and having to plug in? Yeah, root x, I guess, is what we need to take the derivative of. So do it. Do you get?
1/2.
Yeah, 1/2 x to the negative 1/2. Plug in. What are we plugging in? 4, not 2. So is 1/2 x to the negative 1/2.
Wait, 4 to the negative 1/2 is not 1/2. It is.
Do you get 1 for it?
No.
It's a little bit hard to write this, so I'll use Leibniz notation like we did in the warm-up. Or you could use like this, full thing prime. It's hard to, like, there's like a real estate issue in the notation, right? Like f inverse prime, like how do we write that? So we try to avoid the issue. You could like put parentheses around this and say like prime. Or you could use, like I did in the warm-up, you could call it like df inverse dx is 1/2 x to the negative 1/2. Right, I don't know. So a little bit of a notation overload on this. That's the point. But anyway, when you put in 4, when you evaluate that when x is 4, using some superb precalc skills, you get 1/4. Okay. All right. Hopefully, check that. So anyway, does it seem to hold the thing Johnny said earlier from the last slide? Not just with linear functions, but also now we go to curves, calculus style. It seems like our conjecture seems to be holding. It's a little hard to maybe write down in like notation what our conjecture is, but I think we can do it. So here's y equals f of x, or if you, this kind of follows a little bit the proof of the inverse trig functions that we did on Friday, right? We proved some of these. The first thing we did is said like, oh, y equals arc sine x. Well, that means sine of y equals x, right? You see the similarity. Well then, I don't know, what are you going to do next? Keep in mind that we want to say something about derivatives at some point. So differentiating both sides of this with respect to x gives this, but we still have to think about what the derivative of this is. What is the derivative of the inverse of y with respect to x? Well, I don't know. But it's by the chain rule we can write this. And then we have something a little bit strange to say, but we do have 1 over dy dx, right? Which is what we've been saying. It's 1 over the slope from the original function. We just have to figure out maybe what this symbol over here means, maybe. The derivative of f inverse with respect to y. That's a little weird. But it does seem like we're getting like something that makes sense in the previous slide. kind of like what we said, like the answer we got, we still have to think about how to sort this notation out, but it does seem like the answer we get here from this little proof does seem to say what we said on the previous slide, 1 over the derivative we got from before. But, the thing that messes us up on this is not the calculus really, it's just like the notation and the interpretation and all that kind of stuff. So here it is again, this time in, I'm going to do the same picture, but I'm going to generalize, and again, the notation will be the heavy thing here. So the slope that we got here, which earlier was 4, what was that? Well, that was, if we have some function f, that was df dx at x equals, let's call it a. Some x value a. There's a lot of, the notation again is the barrier today to understanding perhaps. Yeah, John.
I was just going to say on the last thing where you like did the final answer
Yeah.
1 over dy.
Yeah.
I thought it might be easier if you like wrote it as dx over dy, because it more easily illustrates how like the derivative of the inverse is like the reciprocal of dy dx.
Yeah, you can write it that way. I think that's not a bad idea. That's an interesting suggestion. I like how you're thinking. So, what's the point over here? If this is the point here, f of a comma a, and how do we say what the derivative is? Well, it's 1 over this, all of this whole. So I don't know how else to write this, and neither does anyone else. So we write this. So what is the derivative here? Well, it's the derivative of this function over here, which is f inverse with respect to x, evaluated at like the y coordinate at f of a. See, the notation is terrible, but there it is in a box. Don't get too bogged down in the notation. As we do this, you'll start to figure out what's going on here. Out loud, I have it written here in quotes. This is the derivative. It says the derivative of f inverse evaluated at f of a, which is what this is, the thing we want maybe, is equal to the reciprocal of the derivative of f evaluated at a. F of a versus at a, right? So the reason this is even something to talk about, you might be thinking, like, why couldn't we have done, like, why is this necessary? Like, why couldn't I just take this derivative immediately? Why would I ever have to do this? The answer is, maybe the inverses may be difficult to find or something. I have this box on the next slide, so didn't quite get all the wording down. I have it again here. So let's try this here. For example, here, I don't even give you enough information. I don't have a function. I just have the necessary information. So the question is find the derivative of the inverse at 5. So you got some curve we're calling f inverse. And we're wondering at the x value 5, if you want, what would the slope be there, given these two pieces of information? Well, if x is 5, you see the x and y thing is messing this up here, but if x is 5 on this function, what we really mean is 5 is like an outputted value from this function, right? So this makes sense over here. What value were we inputting to get 5 on the original function? I guess it's 3. So I don't know. There's not much to do except to write down the answer here. But I just want to make sure you're like clear on why these things connect to the notation up there. Yeah, what's the answer in the end? Yeah, I mean, if the original function has the point 3.5 on it, and at that point the slope was 6, then on the inverse function, make sure you're clear. The place we're asking about is not at x equals 3, it's at x equals 5. And what's the inverse there? What's the derivative there? And the answer is, of course, 1/6. But I just want to make sure you're clear on the how we interpret this box. Okay? Like everything written here is absolutely correct. It's just like notation heavy. Anyway, any questions about the notation there? Okay. Let me give you one, as it might be more commonly seen in the wild here. some of the ones that you have in homework are kind of like this tonight too. So here's a function. There's a point on that function. I didn't have to tell you that, I guess. I mean, you could plug in 1 as easily as I did and find that y is -5 for that x value. So give me an equation of the tangent line to G inverse at the point -5, 1. And again, I don't need to tell you that on G inverse, definitely, the point -5, 1 exists on that function, right? So the first thing you might want is the slope, obviously, at that point. So can you interpret the box well enough to come up with a slope? I'll give you a second. I want you to do some processing yourself. And we'll check together in a minute. You can come up with Don't find G inverse, right? I have up here, why not just find the inverse? Well, anyone who's started doing that right now has already encountered that that's like not a fun task, yes? So can you use the box instead? We have a quick way to do this now. Right? Don't take the inverse. Use the technology, the box we just built out from the last slide. Take the derivative of G and do something with that. All right. Are you get a head start on this at least? So we find the derivative of G is 4x, and so at the point of interest, the slope on G was 4. So let's make sure we say this correctly. What can we say about G inverse? Again, we'll write dg inverse dx. Evaluated at, okay, well I need to know. What's the, I think the answer here is 1/4, right? I think we're clear on that. But what did we just do? 1/4 is the slope where exactly? At -5, 1, right? So it's not the slope at x equals 1 on the inverse. It's the slope at -5. So is this an okay way to write that? Just obey the box that we wrote earlier?
Yes.
So we'll call that like m. Now we're not done. We still need the equation of the tangent line to the graph there. But that's not too bad. So how about you want to give it to us? What's our final answer here? Beautiful, right? Okay. And again, why don't you want to find the inverse? I know some of you started doing that maybe. Anyone who's tried at least a little, waded even a little bit into that can tell us why. Why not? Because it's terrible. I don't know. Right? It's like not fun. And furthermore, sometimes it's perhaps not even possible. And you'll get most of the ones on the homework tonight will be ones that like you couldn't even conceive of how to get the inverse. They're not one-to-one. They're like terrible looking. Yeah. So this will be something. This will not be optional for some of these. On this one, you still could have done it. Right? It wouldn't have been too bad. Yeah. Right.
Homework on the board today was a handout on the website.
Yes, correct.
What is
What is the website?
Right here. The handout is here, and it's taking you. It's got this QR code again. You know how we do. Right? It's technology, you guys. It means you can check your own answers. All right. Have you seen this problem before? Let's try it again.
Or you Snapchat.
Let's try it again.
Snapchat off of Shazam. Snapchat can do everything.
No, it wasn't too painful, Norma. It was okay. It was okay. But let's just verify that the math works here. Let's do it this new way as well and see if you get the same answer as you got in the warm-up.
Yes, that's right. Wait, no, I got negative. Does it sound like there's negative cosine? That's why I have to do half.
Inverse of 1/2 is 2. I just take out the derivative. Yes, it is. It is. All right. All right, I did too. Oh, no, I didn't like study at all. Wait, why did you put it? I was very not. Camera, so you never plug in the light out and we do now.
All right. So could you? Thanks, guys. Could you walk us through this real quick, and then I promise I'll let you get started on the homework here. Yeah, you want to just walk us through here? How do we do this? Using the new technology. You don't know. Piper, you want to bail them out? Go ahead.
The one time I haven't done it.
The one time? Okay. All right. Ben,
Okay, so
walk us through it. What do we do?
okay, so the derivative of sine is cosine x.
Right?
And so basically,
You guys agree? Yeah. Okay.
yeah, so basically I just did 1 over cosine pi over 3, and that gets 1 over 1/2, which equals 2.
Which is what we got in the warm-up. Yeah. All right. So, is that okay? All right. So again, on the homework here, you've got some problems. The 10, they take, you know. Are you okay? Cassie, what's up?
That night, so we won't be trying.
So you won't be giving us homework at home, right?
Exactly. That's fine.
Good.
Better not to be
So as usual, I'd like you to do your work, but then when you're done, you can check your answers on the Visual Calculus website again. Okay? Notice right away that these are functions that you cannot find the inverse of. Yeah.
I'm sorry, I can't pay. Why does it get my way? Wait, why does it get my way? We're at it, here.
Hey, this is not even a warm-up book. No, it's okay.
Start unifying tomorrow.
We just start a warm-up thing that we have and
Let me get you.